Hello, and welcome to my channel. This is a channel dedicated to education, and we try to learn about um, various theories of everything. Um, Also, might want to put that as um, you know, the magnum opuses of people, who spent their whole life working on something, and in general, they never got any credit. Nobody ever knows their name or their theories. But at least I've found something valuable in their work through the research that I've done. And I'm just trying to share these various theories of everything, magnum opuses, cosmologies, um, just different all-encompassing theories. Today is the 324th video that we've done on the reciprocal system of theory, which among all these different cosmologies is probably my favorite. So that's probably why I'm focusing on it so much. The reciprocal system of theory was originated by Dewey B. Larson back in the 20th century up until his death in 1990. And about 60 years before that, he had his first epiphanies about the nature of this universe. And took him about 30 years to work out the kinks and put together his two fundamental postulates, from which he deduced a theoretical universe, basically how the universe operates, if the postulates were true, and then wrote books based on those findings. He's got books on physics and chemistry and astronomy. Also, he's got works on economics and a lot of metaphysical subjects, liberal arts subjects, including philosophy and religion and psychology, even a little bit of stuff on biology. And some of his followers have even gone further afield into crypto-archaeoastronomy and conspiracy theory and, I guess various other occult subjects. Now, the basic idea behind Larson's theory is that we live in a universe made out of motion. It's not made out of matter. It's not made out of energy, but it's made out of motion. And for Larson, motion was the relationship between space and time, with the stipulations that space and time are basically identical to each other, except that they are reciprocals of each other, and they always come as a package deal. There is no independent existence of either time or space. They only exist together in motion. You can think of motion as a fraction, with time or space as the numerator and space or time as the denominator. And you can think of motion in a very broad sense. Larson refers to this as scalar motion. It's a motion that has a magnitude but has no specific direction, which you could envision using a balloon with dots on it, and you blow up the balloon, all the dots are moving away from each other. That's a motion that has a magnitude but no specific direction. All the dots are moving away from all the other dots. So there's no specific direction. It's not a vector. And both time and space have the same general qualities. One being that they are coordinate, meaning that they have 3 dimensions. This is a blasphemy to many physicists out there who regard time as being one-dimensional. But in Larson's system, time has an aspect that is 3-dimensional. And time and space also are progressing. And this is rather blasphemous to the physicists out there who regard space as being stationary. Time, they reckon to be progressing. Time is always getting later and later and later, but in no specific direction. So it's getting later in a scalar manner. But they normally don't think of space as progressing. Don't know why, because the Hubble telescope, way back almost 100 years ago, identified that all of the distant galaxies are moving away from each other. That's a scalar motion outward. And, you know, basically the only reason why we perceive space as being stationary is because we are in a gravitational field. And gravity is the opposite motion as the progression, or a progression, an outward motion. Gravity is that inward scalar motion. And when you are in a gravitational field, the gravity cancels out the progression. So it's not until you have, you're talking about distant galaxies, galaxies that are far away and gravity has attenuated, that you can start to see the effects of the progression. Basically, we see space close up and we see time far away. And that's why we see time progressing in a scalar manner, because we're seeing the very far away view of time, whereas we're seeing a close-up view of space, and so it appears to be stationary. There are other vantage points in the universe where it would be the opposite, and we'll talk about that in just a moment. Then also space and time are quantized, meaning that they come in units. They come in chunks. You have to have a whole chunk before you have any space. You have to have a whole chunk before you have any time. And the chunks are very small, but you know, on the level of the atomic level, they are significant. And if you have exactly 1 unit of space in 1 unit of time, you have the speed of light, which Larson refers to as unit speed. 1 over 1 equals 1. And unit speed, therefore, is really like the background of this reciprocal system, this universe of motion. Or you could call it the 0 point, the ether, the origin. The state of rest of this universe is moving outward at the speed of light in all directions. And that is blasphemous to the legacy scientists also, who, you know, they make their measurements from 0, you know, from no motion. We're going to see how fast this is moving. This is moving compared to 0. But in the reciprocal system, that progression outward at the speed of light is the reference point. So we measure our motion from that speed. And half of the universe, therefore, is moving faster than the speed of light, and half is moving slower. And the scientists only recognize that half that's moving slower than the speed of light. That is what Larson calls the material sector, but he refers to this other sector that the legacy scientists don't know anything about as the cosmic sector. And those two sectors are identical to one another, except that they are reciprocals. And you need to be able to interchange the roles of space and time to move from one sector to the other. So in the material sector, as we said, we see space close up. Space is stationary, 3-dimensional coordinate, and time is progressing. So we see time far away. and it's progressing in a scalar manner. It's always getting later and later and later and later. But if we crossed over into the cosmic sector, we would see coordinate time. We would see time up close, and it would appear to be motionless. And then we would see space as progressing. Things are always getting farther and farther and farther apart. And so we would be seeing space far away and time up close if we were in the cosmic sector. And then there is two other boundaries. So there's really three major boundaries in the reciprocal system. There's this first one, the unit speed boundary, the speed of light boundary, and that divides into the material sector and the cosmic sector. But then within the material sector, we have what is called the unit space boundary. If you don't have a full unit of space, you don't have space. That is the discrete unit postulate, part of the first postulate of the reciprocal system. You have to have a full unit before you have anything. So if you don't have a full unit of space, you don't have space. And if you don't have space, then you only have time. And so in this realm of less than 1 unit of space, and 1 unit of space is approximately, I believe it's like 1/500,000th of an inch. And so if you're dealing with less than that, you don't have space. And so you are in this realm of only time. Larson refers to this as the time region. And the time region is really the realm of your atomic and molecular activity. And also when you cross that boundary, just like when you cross the speed of light boundary, the rules reverse. And you're in this realm of time instead of being more in the realm of space. And the same thing occurs over in the cosmic sector, but with time, within 1 unit of time. Now, 1 unit of time is the incredibly brief period of 1.52 times 10 to the minus 16 seconds. So you can fit 6.576 quadrillion of those units within 1 second. And a quadrillion is basically a billion million, and or a million billion. And within, if you don't have that full unit of time, then you don't have time by the discrete unit postulate. And so you only have space. So you're in a realm of space only. And if you're in this realm of space only, you are basically, again, dealing with what Larson calls cosmic atoms and cosmic molecules. These are referred to by the legacy scientists as antimatter. And the legacy scientists have come up with a number of different convoluted theories to explain this. But Larson has something quite a bit more straightforward. They're just normal matter, but they're in the cosmic sector. And occasionally they come across into the material sector and interact with us. But when they come across into the material sector, they immediately start to decay because they are unstable in this environment. Just like when we would cross the speed of light boundary and go into the cosmic sector, we would have trouble maintaining our stability. Okay, now what we're doing today is we are reading over the next portion of this paper that Larson wrote that is called The Nature of Time. And we read the first installment of this yesterday. So if you want to go back to the beginning of the paper, you want to go back and watch yesterday's episode. But we will start here. In the first part of the paper, he basically just went through and looked at how legacy science really has taken the time phenomena for granted, and that they have not rigorously defined what time is. And Newton, he quoted Newton, and Newton said, time being one-dimensional, that being known to all, or something like that. It's just like, we're just assuming that time is one-dimensional. Everybody knows that. If you study Tree of Life, or if you watch any of my Tree of Life videos, that's like the eighth sphere. It's the consensus worldview. Everybody knows that. So therefore, we don't have to, prove it or show it or demonstrate it or anything. You just have to assume that. And Larson is showing how foolish that is here in the first part of the paper. So now we're moving to the second part here. As a general proposition, the superiority of this approach is not open to serious question, but a direct extrapolation does not appear feasible in this case, as we have no positive knowledge as to what the properties of space and time actually are anywhere, and consequently, there is no adequate base from which to extrapolate. All previous investigators have therefore relied upon assumptions, some related to our rather vague general impressions of space and time, others wholly conjectural, not because they preferred to do so, but because they felt that they had no option. The method which I have employed to overcome the existing difficulties is to approach this question indirectly, beginning with an examination of the relation between space and time. This relation is one that has never been adequately explored heretofore. In the days of Newton, its existence was not recognized at all, the two entities being regarded as completely independent. Since then, there has been a growing realization that they are not independent, and that basically we must deal with space-time, not with space and time individually. Thus far, however, it does not appear to have been suspected that the existing concepts of the fundamental nature of space and time may be in error. That time, for instance, may be actually something other than a unidirectional, one-valued, one-dimensional continuum. And the hypotheses that have been advanced as to the character of the space-time relation, such as Minkowski's concept of a four-dimensional continuum, have retained these basic assumptions and thus have simply applied speculation upon conjecture. Instead of starting with arbitrary assumptions, the first move in the present investigation has been to extrapolate to the universe as a whole the relation between space and time, which we find existing in the known region of the universe. In this known region, the relation between space and time is motion. And in motion, space and time are reciprocally related. Now, just think of the concept of speed. The car is moving 15 miles an hour. 15 miles of space in 1 hour of time. Space over time. Space divided by time is speed. So there we have a reciprocal relationship between space and time. So he's saying that that is the common understanding that we have of motion in this known region. And so he's saying that, like, in common knowledge, space is reciprocally related to time in motion, particularly in speed. And so he's saying that now I'm going to extrapolate what we know about this known region to these unknown regions of the universe, and I'm just going to, kind of use the hypothesis that space and time are reciprocals of one another in the whole universe, because I know that they are in the known region. Okay, and this is not surmise or assumption, nor is its accuracy in any way open to doubt. It is positive knowledge from which we can extrapolate. Irrespective of the nature of the properties of space and time individually, the method of extrapolation leads directly to the conclusion that we should postulate a general reciprocal relation between space and time effective throughout the universe. Of course, any new viewpoint that conflicts with long-standing beliefs concerning space and time, no matter how firmly based it may be, will seem strange and hardly credible on first consideration. But nothing that we actually know about space or time is inconsistent with this reciprocal postulate. The truth is that we know very little about either of these entities. Time, no quote. Time has always been mysterious and elusive, but even space, which seems so much more understandable, has been a difficult problem for those who have sought to discover its true nature. And no general agreement on this score has ever been reached. To Aristotle, space was merely a relationship between physical objects. To Democritus and his fellow atomists, it was a container in which such objects exist. To Einstein, it was a medium connecting these objects. Certainly, it cannot be claimed that there now exists any positive knowledge about the inherent nature of space, to which a new theory must conform. On the contrary, the conclusion of this current investigation, which in effect asserts that space is merely an aspect of motion, has a much greater a priori probability of being correct than any of its predecessors, since it has been reached by way of a more reliable process. Nevertheless, the proof of the pudding must be in the eating. That is, we must develop the consequences of the new concept and see whether they give us a more logical and consistent picture of physical relations than the currently accepted ideas. It will not be possible in a short article of this kind to describe all of the results that have been obtained in the application of the reciprocal hypothesis to a wide variety of physical phenomena during the many years that this investigation has been underway. But the general nature of the results can be demonstrated by a typical example, and in the discussion that follows, the consequences of the reciprocal postulate will be developed far enough to produce an explanation of gravitation, something that no other physical theory has been able to do. The gravitational findings are particularly interesting because they not only demonstrate the ease with which this new development surmounts the difficulties that have stood in the way of progress in such areas as this, but also show why we get a distorted view of space and time from our everyday experience, and why most of the inferences as to the nature of these entities that we draw from such experience are erroneous and misleading. No doubt many readers will be surprised at the assertion that gravitation still remains unexplained, as there is a very common misconception that Einstein's general theory of relativity supplies such an explanation. But, as Willem de Sitter has pointed out very clearly, no hypothesis thus far advanced to explain gravitation has ever had the least chance. They have all been failures. Einstein's contribution, de Sitter says, is to make gravitation identical with inertia, and thus to put it in the category of one of the fundamental facts of nature which have to be accepted without explanation, like the axioms of geometry. After 50 years, the inadequacy of this treatment is clearly apparent. As R.H. Dick puts it, gravitation is still an enigma, and it may be well the most fundamental and least understood of the interactions. A recently published review of the proceedings of the first Soviet Gravitational Conference confirms this opinion with the following comments. The gathering seemed painfully perplexed with endless questions, nearly all of which remain unanswered. The crux of the gravitational problem is the dilemma which no previous theory has been able to avoid: the apparent necessity of postulating either action at a distance, which is philosophically unacceptable to most scientists, or propagation through a medium, which is completely lacking in observational support and is faced with seemingly insurmountable practical obstacles. After 300 years in which it has been agreed that these are the only two possibilities, the new development based on the reciprocal postulate now produces a third alternative that has been completely overlooked by previous investigators, one in which gravitation acts in a perfectly natural and understandable way, instantaneously, without an intervening medium or a medium-like space, and in such a way that it cannot be screened off or modified in any way, all of which are exactly in accord with what our observations have indicated. To begin the explanation of how these results were obtained, let us now return to the basic assumption of the reciprocal relation between space and time. It is evident that this assumption necessitates a further postulate that space and time have the same dimensions, since quantities of different dimensions cannot stand in a reciprocal relation to each other. We can recognize 3 dimensions of space, and with the simplest assumption that is consistent with both the reciprocal postulate and the observed properties of space, is that both space and time are 3-dimensional. Limitations of both space and time to discrete units is also necessary in order to make the reciprocal postulate mathematically workable. Extrapolation of the relation between space and time that is observed in the phenomenon of motion thus leads directly to 3 conclusions about the properties of time and space, which can replace the assumptions that the physicists have made with, quote, without examination, together with the further assumption that space-time, as thus defined, is the sole constituent of the physical universe. These can be combined into one comprehensive postulate as follows. And so this is Larson's first fundamental postulate. The physical universe is composed entirely of one component, motion, or as he called it, space-time. So the physical universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and in 2 reciprocal aspects, or 2 reciprocal forms, space and time. Okay, we're going to leave it off there. I think I'll probably start up tomorrow and read that first fundamental postulate again, and then we will eventually, he will explain that a little bit and go into the second postulate a little bit. But, you know, again, that's, he's using the postulate as a hypothesis, but he's explaining, you know, where this is coming from, basically a process of extrapolation. We've determined that time is 3-dimensional, or that space is 3-dimensional, so we're going to extrapolate that to space. And we've determined that motion is the relationship between space and time, which creates a reciprocal relationship. If you have a reciprocal relationship, they need to have the same dimensionality. They also need to be in discrete units. And then if we have so if we have three, so they are both three-dimensional, and they both come in discrete units, and they both are reciprocals of one another. Okay, we will resume this article tomorrow, and I appreciate you tuning in today.